HDR, or high dynamic range, has been used extensively in the world of photography for years. And over the last 10 years, HDR has been introduced to video content to give us a far deeper image quality and definition, especially noticeable on larger panels, which have become today's norm. This course will explain HDR technology and give you clarity on exactly how it improves the quality of an image. Put simply, HDR improves the quality of an image by creating whiter whites and darker blacks, while making millions more colours appear on the screen. By increasing the contrast and brightness capabilities of a display, we're able to make a far wider range of colours and colour shades available. In other words, by increasing brightness and contrast levels, we're able to display deeper and more vibrant shades of blue, green and red across the screen, because the range from dark to light is far higher in a display that can support HDR. In the Colour Space and Colour Depth course, we introduced you to the chromaticity chart to explain the differences between Rec 601 or standard definition, Rec 709 or high definition, and Rec 2020 or ultra high definition. You can revisit that course by clicking here in the top right. We're going to use the same chromaticity chart to help us explain HDR, because while it's not a direct component of HDR, WCG or wide colour gamut describes the amount of colours which can be shown at any one time on a display. And once you understand this, you'll have more clarity on the benefits of HDR. The brightness of a display is measured in nits, and when the technical wizards of yesterday went to work making HDR as effective as possible, the standard definition technology available forced video content to be produced to meet the requirements of the typical CRT TVs available using the Rec 709 colour gamut and brightness of around 100 nits. Contrast this to the human eye, which can perceive up to 10,000 nits of brightness. With SDR's limitations, content creators had to carefully choose how to squeeze a realistic image into the 100 nits of brightness available. It's no wonder you've never confused a TV screen with reality. HDR has dramatically changed this because content is being produced using a colour gamut and a peak brightness which is more similar to the capabilities of the human eye. However, not all HDR displays and formats are created equally, so content may include wider colour gamut and higher peak brightness than the display's capabilities. Metadata is the term used for embedded information about the content, which helps a lower brightness display understand how to successfully display a high peak brightness image. The world of video has become a lot more complicated. If the metadata wasn't present, then the display wouldn't know how to correctly show the HDR content it's receiving. For example, a media container used for HDR can carry more saturated colours than can be shown on most wide colour gamut displays. Therefore, the media container is larger than the display's native colour gamut, and that content needs to be precisely mapped to the capabilities of the display. HDR itself is managed in a number of different ways. HDR10, HDR10 Plus, and Dolby Vision. Now, these all work in similar ways by increasing the contrast and colours. However, they do behave differently. HDR10 is a popular and simple HDR format developed by the Consumer Technology Association. The HDR10 standard sends static metadata to the display, enabling the display to calibrate its picture based on overall characteristics of the video stream. HDR10 aims to produce around 1,000 nits of peak brightness. HDR10 Plus was developed by Samsung and Amazon, and HDR10 Plus works differently to HDR10 by sending dynamic metadata, allowing TVs to calibrate the best possible picture frame by frame. This makes the picture look more realistic, and the format supports brightness values up to 4000 nits. HDR10 and HDR10 Plus both send their metadata from source to display using data parsing mechanisms in the HDMI standard called AV info frames. And it's these two formats which are commonly used by film production companies, video game manufacturers, and TV show production companies. Finally, Dolby Vision is a proprietary HDR standard introduced by Dolby Laboratories. Like HDR10 Plus, Dolby Vision also sends dynamic metadata to the TV and further supports 12-bit color depth, which is 4096 shades of each primary color. Dolby Vision aims at reproducing 10,000 nits of peak brightness, far more than that which is offered by its counterpart HDR standards, suggesting that TVs with Dolby Vision can produce 10 times the amount of light than HDR10, although there are currently very few displays that can actually support a 10,000 nit brightness value. Dolby Vision parses its metadata by encoding and hiding the metadata inside the image itself. In HDR10, HDR10 Plus and standard Dolby Vision, the data transmitted from the source to the display is identical regardless of the display. And it's the display using metadata which adjusts the image to suit itself. The latest iteration of Dolby Vision is called low latency mode. And in this mode, the source reads out the detailed HDR capabilities of the display via EDID, and then passes a customized signal built specifically for that display. The same source would pass different signals when connected to different displays. Because the TV is receiving a customized signal already, there's no need for metadata in Dolby Vision low latency mode, so none is passed. So, the next time you see the phrase HDR compatible, you'll be able to appreciate just how much work goes into making your display provide you with images which aim to meet the high peak brightness demands of your eyes. The idea of a source customizing its data for a specific display brings up specific challenges for video distribution systems, and we'll learn more about that in our next HDR installment.